Hello everyone, this is Ramiz Halloum, a research scholar at the High Voltage Lab in the Indian Institute of Science under the guidance of Dr. Subbareddy. My topic is about the performance evaluation of the newly developed FRP rod used in outdoor composite insulator using the rotating wheel and dip experiment. This slide shows the main outline of this presentation. So let's start with the introduction. The use of composite insulator is increasing more and more in power and transmission system because of their superior characteristics, especially the drastic weight reduction. It may go up to 90% compared to the ceramic or glass insulators. Also, it provides a high mechanical strength and also improved pollution performance due to the hydrophobic nature of the silicon rubber. The main components of these polymeric insulators are the FRP rod, silicon rubber housing, metallic end fittings. The FRP rod provides the internal insulation and also the required mechanical strength. The silicon rubber housing provides the required cribbage distance to limit the leakage current and also protect the FRP rod against the various electrical and environmental stresses. Silicon rubber is made of the PDMS with some added inorganic filler like SATH or silica fillers to improve the mechanical and electrical characteristics, whereas FRP rod is made of the epoxy resin matrix with glass fiber. However, these new insulators show some drawbacks, especially the long-term performance and reliability, degradation and aging under the action of the electrical discharges due to the organic nature, electric field enhancements near the end fittings, especially the high voltage end, and also FRP rod fracture, which may lead to a complete shutdown of the transmission line. So there are two types of the FRP rod fracture which are well known, which is the normal fracture due to the higher mechanical strength than the rated value, or the brittle fracture, which is due to the stress corrosion crack of the glass fiber. However, a new type of the FRP rod fracture has been reported in many countries, which is known the decay-like fracture. This new type of fracture is mainly due to the degradation of the epoxy resin matrix under the action of the electrical discharges and also due to the water and acid penetration through the silicon rubber housing. So in this study, we evaluated the performance of the FRP rod using the rotating wheel and dip experiment as per the IEC standards. This experiment is consisted of 4 stages. The first stage is dipping stage, where the sample or the FRP rod will be dipped in a contamination solution made of the tap water and the NaCl to obtain the required conductivity of 2.2 microsiemens per centimeter. Then dripping stage for 40 seconds also. Then the high voltage energization, where the high voltage will be applied on the sample for 40 seconds. And at the end, we have a cooling stage for 40 seconds. The period of each stage is 40 seconds with 8 seconds transition time. So the total cycle time will be 192 seconds. So this experiment is conducted on the bare FRP rods samples for 1046 hours to evaluate their performance under the worst case scenario, where the FRP rod will be exposed to conducting water film and electrical discharges. So the circuit diagram of this experiment is shown here. So two different FRP rod samples were used in this experiment. The first one is the normal FRP rod, and the second sample is the newly developed tracking resistant FRP rod, which are provided from the manufacturer. So the applied voltage was based on the dry arc distance, which was about 250 mm for both samples, and the applied voltage was about 9 kilovolt. The thermogravimetric analysis was conducted on the FRP rod to determine the content of the epoxy resin and the glass fiber, since the thermal stability for the epoxy resin is much lower than the glass fiber, which is about 1600 Celsius. So as we see here, the epoxy resin content in the normal sample is higher than the tracking resistant sample. So this figure shows the both samples during the experiment and also at the end of the experiment, where we see here clearly that tracking started in sample A normal FRP road at about 300 hour. Also, the electrical discharge at the triple junction, due to the electric field enhancement at this point, it appears much early for the normal sample at 48 hour compared to the tracking resistant sample at 264 hour. In addition, also the dry bands along the surface of the FRB rod appears also in sample A much earlier compared to the newly tracking resistant FRB rod. No tracking was observed in the sample B during the experiment. This figure shows the leakage current of both samples during the experiment, where a significant increase in the leakage current is seen for both samples, which is mainly because of the decrement of the surface resistance as a result of the degradation of the FRB rod surface under the action of the electrical discharges. However, this increment was higher in normal sample compared with the tracking resistant sample, indicating a significant degradation in the normal sample compared to the newly developed sample. So now the scanning electron microscope equipped with energy dispersive X-ray detector was used to evaluate the surface morphology changes, any morphology changes or the elemental composition on the surface of the FRB rod samples. For the fresh sample here, we see that the glass fiber are well covered by the epoxy resin matrix, and also the interface between the glass fiber and the epoxy resin is well and intact. However, after the experiment in the normal FRB rod, sample A shows a severe degradation where many glass fibers are found to be broken and separated from the epoxy resin matrix, and also the remaining epoxy resin matrix was found to be uneven and eclastic with many holes, which could be due to the gas generated during the degradation of the epoxy resin under the impact of the electrical discharges, arcs, leakage current, etc. However, the newly developed tracking resistant FRB rod shows a superior performance and less degradation, where the glass fiber is still covered with the epoxy resin with slightly more rough texture in the epoxy resin. So this table now shows the atomic elemental composition on the surface of the FRB rod samples, both fresh and aged. So now, as we see here in the normal FRB rod sample a significant decrease in the carbon content is seen, and a significant increase in the oxygen content also is seen, which could be due to the oxidation process taking place under the impact of the electrical discharge, leading to the decomposition of the epoxy resin into water and carbon dioxide, and leading to this significant decrement in the carbon content. However, this carbon decrement in the tracking resistant FRB rod was found to be less. In both samples, also nitrogen was detected, which is an evidence of the nitric acid formation under the impact of the electrical discharges. However, this content of nitrogen content was found to be more in sample A, which indicate that more severe electrical discharges took place in the normal FRB rod sample. The sodium content is increased drastically in both aged sample, which could be from the contamination solution, which was made from the NaCl with tap water. Also, the silicon content was found to be higher for both aged sample, which could be because of the breakage of the SiO bond in the glass fiber under the impact of the discharges activities. Finally, the content of the metallic elements such as the magnesium is increased because of the ionic exchange with the free hydrogen ions when the FRB rod subjected to water or the nitric acid. FTIR analysis is conducted on both fresh and aged FRP rod samples to identify the molecular bonding over the sample surface and to determine the degradation level. This table showed the important chemical bond in the FRP rod with the corresponding wave number. So the transmittance peaks corresponding to the aromatic structure, methyl and aliphatic groups is found to be more in the fresh sample A compared with the fresh sample B, which indicate that higher content of the epoxy resin. This agrees with the TGA and also EDS analysis before. Also, the epoxy resin in sample A, the normal FRB rod was found to be more severely degraded, as the corresponding peaks of methyl aromatic structure and also aliphatic groups was drastically reduced compared with the trekking resistant FRP rod. In addition, also an obvious reduction in the transmittance peak corresponding to SiO bond in the glass fiber, which indicate that a severe and hydrolysis and ion exchange of the glass fiber in the sample A compared with the sample B. Finally, the absence of the spectrum peak corresponding to the ester group is in sample B is due to the absence of the coupling and curing agent. This slide shows the conclusions of the work where the new trekking resistant FRP rod shows a superior performance compared with the normal FRP rod, where trekking takes place in the normal FRP rod after about 300 hours near the ground electrode with significant increase in the leakage current and also the discharges activities. Both SEM scanning electron microscope and energy dispersive X-ray spectroscopy analysis showed that the significant deterioration in the epoxy resin matrix in the normal FRP rod with many fractured glass fibers and also hydrolysis ion exchange were more severe in the normal FRP rod. And also the FTIR analysis showed that a significant degradation in the epoxy resin matrix was detected in the normal FRP rod compared with the trekking resistant FRP rod. Thank you. Please, any question?